Hola, ¿qué tal, Leonardo? Buenas tardes.
Oh, hello, hello,
Hello.
hello. Um, so should I start sharing my screen?
Yes, please.
Just wait a moment. Yes. Oh, here it is.
Yes, we can see it
And
now.
great.
Good, Leonardo. By any chance,
Well,
you speak Spanish?
no, I don't speak Spanish. I'm Brazilian,
Okay,
actually.
okay, okay. We thought you were from Spain or Mexico or something.
Oh, no, my
But
surname
it's
is
not a problem.
Spanish, but
Yeah, it's not a problem. Good. If you don't have a problem, we can wait a couple of minutes.
oh,
Meanwhile,
that
more
yeah,
people arrive.
yeah. Let's wait a little bit. That's fine for me.
Okay, thank you.
Los cuales serían Facebook, WhatsApp, Twitter, Instagram y Snapchat. Además, también contaría con lo que sería Uber, tanto como conductor y pasajero.
Uh, 1 second more,
Oh,
Leonardo, please.
oh, okay, that's fine.
Thanks. Sí, sí, adelante. Okay, good afternoon, everyone. Good afternoon, Leonardo Pacheco. The following talk is presented by Leonardo, whose title is Game Semantic for the Constructive Mu Calculus. Go ahead, Leonardo, please.
Thank you. So today I'll be talking about game semantics for the constructive mu calculus. So just before we start, the mu calculus is an extension of modal logic by fixed point operators. In this talk, I'm gonna talk about this extension, not over the standard usual modal logic, but modal logic with constructive semantics. So before I talk about calculus, I'll give a little short review about constructive modal logic. Then I'll explain the mu calculus and its game semantics. And in the end, I'll show one application. We can use this game semantics to study a constructive version of S5 with fixed point operators. So let's begin with the modal logic. The basic logic we can think of for this constructive modal logic is going to be this logic CK. This was defined by Mendler and DePaiva in 2005. So the axioms of this logic consist of all the intuitionistic tautologies with a version of the axiom K, the basic axiom of normality. But here we require these two parts. One from box phi implies psi, we get box phi implies box psi. Along with from box phi implies psi, we get diamond psi implies diamond phi. These two things are equivalent in the classical setting, but here for the constructive setting, we won't get this equivalence. So we need both of them. And this logic, CK is going to be closed under the necessitation as usual. If we have phi, then we have that phi is necessary. And modus ponens. From phi and phi implies psi, we get psi. So that's the axiomatization. Essentially, we're changing from having classical tautologies to having intuitionistic tautologies. So, okay, let's take a look at the semantics. The semantics are going to be similar to the usual semantics, but now we're going to have a little bit more things inside our Kripke models. So now we're going to have 5 things inside the Kripke models. You're going to have a set of possible words as usual. You're going to have some modal relation as usual and evaluation. But we also add now 2 things. First, we have this set of valuable words. This is going to be a subset of the possible words where the proposition, like if some word is inside this is valuable, then we'll have that this word will satisfy the proposition false. So you get that this is going to be like an inconsistent word. And we have another relation that we call the intuitionistic relation that's modeling the constructive / intuitionistic part of the calculus. So you can think this as like an increase of information. If W comes before V, then V, everything that holds at W is going to hold at V too. And this is similar to how we model intuitionistic logic with Kripke models. But now we have these 2 relations. We have one little requirement that we require that the composition of the model relation and the intuitionistic relation is going to be a subset of the composition of the intuitionistic then the model relation. And we now can define implies and negation and disjunction as usual, we have in on intuitionistic logic with Kripke models. We just need to take a little bit more care with the boxes and diamonds. So we'll have that phi is necessary, like box phi holds at some word W if and only if for all word where we add more information, and for all word accessible from this word V, we have that U holds at psi. And diamond is similar, that we have that for whichever way we add information, there's gonna be some accessible word where phi holds. And okay, we define the semantics like this. We have the proof system like before, and we'll have that the proof system CK we had is gonna be complete over these constructive cryptic frames. So okay, we can already think of a game semantics from the point of view of model logic. Now there is still not that interesting. We don't get that much, but let's set up everything for now. Let's say that we have a formula, we have a constructive grouping model and some word. We can define some evaluation game to check if this formula phi holds at the word W. So, okay, this game, you have two players. You have players 1 and 2. These players will have roles as verifier and refuter. One is going to start as verifier and 2 as refuter. And whoever is verifier at some point of the game will be trying to show that some formula holds at some word. And the refuter is going to try to show that some formula fails at some word. Which player gets to make a move? Well, it depends on whichever formula you're thinking about at the moment. Here are some examples. Say the players are discussing whether psi and theta holds at W. For this to fail, you just need for one to fail. So, okay, the filter is going to choose one of psi and W or theta and W to show, oh, I think psi doesn't hold at W, or I think theta doesn't hold at W. And like this. For the diamond case, it's a little bit more complicated. Remember the definition we saw the last slide? And here, if you want, the players are discussing if diamond psi holds at some word W. So refuter is gonna pick somewhere accessible from W via the intuitionistic relation, this word V. And then verifier is gonna pick some U that is accessible via the model relation from V. And the players move to this word. And the box is similar, but the refuter is gonna pick twice. And now that the part that complicates the games for us is that at negations, we'll have that the players are gonna switch roles. So if one is verifier in this state, and they move, and then the next play they're gonna switch. So one is now refuter, and they're gonna discuss this. And here's still not that messy, but at the mu calculus is where things get interesting. And for completeness, I'll say if the players are discussing if some proposition word holds at some word, they just look at the valuation. And by for the model case, we can show by induction that phi is gonna hold at W if and only if verifier wins this evaluation game. So they have a way of playing the game that guarantees that they're gonna win each play they do. So, okay. And before we go to the mu calculus, one little aside. There are lots of variations of constructive model logics. I picked CK because it's the most basic, but you also have some two other that are quite famous. You have this intuitionistic K, that you had these other axioms here, and you have a Godel K, that you have a linearity axiom, and all of these are going to be complete over certain classes of constructive cryptic frames. But we won't go into this today. So, okay, let's take a look at the mu calculus. So the mu formulas are going to be defined by this grammar. You have proposition symbols, you have variable symbols. These are essentially special proposition systems we use to set up the fixed point operators. You have false, you have true, You can have negations, conjunctions, disjunctions, implications, and boxes and diamonds, and the least fixed point operators, mu x, and greatest fixed point operator, mu x. There's a small detail I'll comment later, but these two formulas, these two times their formulas are not always defined. You're gonna require that x is something called positive in phi. This is so that the semantics is well behaved. Let's not think too much about this, and we'll come back to it later. So now, say we have some formula, psi x, we're gonna define this operator, gamma of phi, that takes a set A into the sets of words of some model where psi A holds, like psi A in the place of x. And this is a fixed point. This is an operator taking sets of words into sets of words, if we have fixed this model M. And we'll have that a word satisfies this mu x if and only if this word is in the least fixed point. And this word is going to satisfy mu x if and only if it's in the greatest fixed point operator. And what positiveness comes, it's going to guarantee that we can take this fixed points exist. We'll take a look at it later. Now, let's take a look at one simpler example first. Sorry. So now fix on Ripke model. We are going to try to evaluate this formula, mu x of PR diamond x. And this is going to be the fixed point of the operator that takes A to PR diamond A. So, okay, we can approximate this fixed point from below. We just get nothing and apply it once and apply it once more, apply it once more, and keep doing it. So we get empty sets and P and M and P or diamond N or P or diamond P, and so on. So in this end, this formula is going to be equivalent to this this formula, which is not a formula in the grammar, but you can think like eventually P is accessible. So you can do this approximation. And okay, we can think this on the setting of the game semantics. So now for the formulas of the mu calculus, for the model logic we have as always, and let's think about the evaluation game for this. We need to add two rules more, and one is from some word, if your evaluation the mu formula and some word, you just move to the formula inside. So you throw away this fixed point operator. But now we also have a variable. From this variable evaluation, if it holds on some word V, you go back to the full formula. And you want this game to be finite, because the verifier is going to lose the game. By definition, the verifier is going to lose some infinite play if and only if this mu x appears infinitely often. So that's the condition. So if the game goes on and mu appears infinitely often, the verifier loses. And you get something similar that if you have some formula with just a new operator, then on an infinite play, verifier is going to win if and only if it's regenerated infinitely often. But now comes the interesting part of the semantics of the mu calculus. We can have more than one fixed point operator mixed together. So let's take a look at this formula with a greatest and the least fixed point operator. So this set here will be the least fixed point of this operator. You're going to take a set, and this is going to be a least fixed point operator. We can again try to approximate this fixed point. We cannot just straight advance. We have to do it with a little more care. So now this is the greatest fixed point. We start with everything and go trimming down. So we have x0, and this is the set of all words. And that we make y0 be the least fixed point of this operator. Gamma phi with x0 in place of x this is fixed, and y. So this has just one free variable. And then we apply gamma 1s on this thing. So we have x1 is going to be phi of x0 and y0. And then we try to make another y. And we repeat and we repeat and repeat this. And this goes transfinitely often. These ordinals here may be quite big, as in this is already two fixed point operators. We can already get non-admissible ordinals. So let's just say that those are quite big, if you don't know what they are. But you get something like this. So you can do this approximation and say that you have, I don't know, some 100 of these alternating least and greatest fixed point operators. Well, you have to you approximate the first and then one step in the second, approximate the first, one step in the second, and then you repeat this until you get a fixed point for the second, and then you do one step on the third, and then repeat and repeat and repeat. And if you have lots of fixed point operators, it gets very complicated, very hard to handle. And that's where we use the game semantics. Please ignore the table down for now, but if we have more than one least and greatest, we can think in a little more simpler way than looking at the fixed points. You can try the semantics, and we'll have that. Let's say we have an infinite play, and we let this eta x psi be the formula which came back in one of from the formulas that came back infinitely often. They're the one with the biggest scope. And now we get the player with the role of verifier at the place of these positions of this form, like from this formula with biggest scope, evaluation this formula with big scope. If it is, this eta is a null, then verifier is going to win. If it's a mu, then refuter is going to win. And when proving things about the mu calculus, it's way easier to use this than to use the official semantics. Just for reference, this is the set of all the rules. It's a little bit not that pretty looking game, but it is good to work with. So that's more or less the semantics. And the proof of the idea of the proof is essentially trying to think about this. For the new, you don't want it to repeat infinitely often. For the new, you want, and so you can control the ordinals where the approximation stages, which are going to be the least, where some formula is going to hold or not. So, and yeah, I said about positiveness. There's a technical point. Don't think too much about this, but this variable x being positive in a formula means that the fixed point operator is going to be monotone. And so you can just do this approximation of the fixed points. You can also think about fixed points of non-monotone operators, but this is also quite more complicated. And the idea is essentially, you could, in the classical setting, this would be just saying that x is in the scope of an even number of negations. Here we need to take more care. But only the negation case, if you're thinking of the negation case, it's still simple. So, okay, now let's take a look at this constructive version of S5 and see how we can use this game semantics to study it with these fixed point operators. So CS5, we get it by adding to CK the add actions for T, 4, and 5. Again, on this constructive setting, we need to add both the contrapositives. We have, for example, 4, it is usual to adjust the diamond box and box phi and 2 box phi. And in the classical semantics, we would already have diamond phi implies diamond psi, but those two are not equivalent here. So we had to add both. And a CS5 model is just going to be a constructive model as we had before, but will require that this relation R is an equivalence relation, similar to what we would have in the classical S5. Okay, this proof system, this axiomatization is going to be complete over these models. This is a theorem by the Fisher server, I think from the 60s. And we can think about the mu calculus over these models. Over these models, we can show that the mu calculus is going to be equivalent to model logic. We say it collapses to model logic. Why? Just a brief idea of why this holds. We have that if we have this CS5 model, and from W, you can advance via the intuitionistic relation, and then via the model relation, you get to W prime. Then if some box phi or diamond phi hold at W, then it's also going to hold at W prime. And so we can think about an evaluation game and say, for example, with UX and the psi is in the scope of some box. You have something like this, and say you have a long enough game. If it's a short game, then you just cut it over, it won't be a problem. But if it's a long game, then if verifier wins here, they're also going to win here. But if refuter wins here, they were already going to win here. So you can use this to show like this tail here is not going to matter much. You already have all the information from here. And we can use this to show that two iterations of the operator, like phi of phi through, are going to be equivalent to 3 iterators. So instead of this formula, we can just think about this formula with a little bit more care, but the key idea is essentially this. You have an infinite game, it's going to be repeating, and you can show, oh, we don't need this infinite game. We can think about a shorter one. So with this, we can think about this version of CS5 with fixed point operators. We could add, we get this by adding these actions for fixed point operators. That these two things are gonna mean that new x5 is gonna be the greatest fixed point of the operator, gamma phi, and these are the rules for the list. And we can show that, yeah, this mu CS5 is complete over the CS5 frames. All the things with fixed point that hold are going to be true, and they're going to be true if they hold. And we do this using both the collapse to model logic, showing that the phi of bottom is going to be equivalent to phi of bottom, and the same for true. And the completeness for CS5. Then we have this equivalence, and we have it in the system, and then we can use these axioms and rules to, with these equivalences, to throw away the fixed point operators. So yeah, honestly, this system is not that interesting from this point of view, but yeah, we get this elimination, and it is kind of weird because usually this kind of collapse, it doesn't happen at all when we have more than one modality. And here we have kind of two. And I think that was it for today. So I talked about this game semantics and showed that the mu-cox collapses and mu-CS5 is complete. And well, this is a big open. So next type is I have this proof system for the constructive mu-calculus, and I have the constructive cryptic frames. I still don't have a proof for this completeness, but it's one thing I'm working on. And there are other things that are easy to show on the classical semantics, but things break down on the constructive case. And if anyone is interested in more details, proofs, and references are in this preprint. Game semantics for the constructive mu-calculus, same title as the talk. It's on archive. And that's it for today. Thank you.
Thank you so much, Leonardo. Now we will open the floor to our audience for questions. Does anyone have a question? Go ahead, Fabio, please.
You hear me?
Yes.
Sorry, I was a little late. I was in the wrong link. I have a curiosity. When you define the game semantics for the fixed points,
Yes.
I don't know if you can put that slide.
This one?
The evaluation, the game.
Oh,
I think the first one.
here? This?
Yeah, I think that one.
Yes.
The next one. The
This
next
one?
one. I think, yeah, the second item,
Yeah.
because the first one is, but also the first one. Usually, and in your last system, usually when you have the fixed point, you have either the fold or the unfold of the fixed point.
Yes.
And here you move from the fixed point, you only eliminate the fixed point operator, but you don't do the unfold.
Yes.
And in the second item, you start with the variable. Not, I would expect, as in the last slide, to move from the fixed point to the unfold, and from the unfold to the fixed point. So I don't know if you have some intuition about this definition.
Yes. That's a thing you could do. You could move to the unfold. But I think this way of setting up the game semantics makes a little easier to define it. Because you could do it also. The biggest change is that instead of talking about this operator being regenerated, you're gonna talk about it being unfolded. And for the full definition, you'd have that from the operators being unfolded with the biggest scope, verifiers want it to be a new. And yeah, you can do the same.
Okay, so
I think it's just
it's only
Merkle.
because it's easier this way.
Yes. And at least in the new calculus setting, it's a traditional way of doing things. I'm not exactly sure why.
And this eta x that we have here in this slide is only an arbitrary fixed point, which is between the least and the greatest, yeah?
Yes, yeah. It's either mu or it's new.
Okay, yeah. Thank you.
Thank you.
Okay, thanks. Does anyone else have a question? Okay, once again, we express our gratitude to Leonardo for his valuable participations. Thanks, Leonardo.
Thank you very
now,
much.
It's Bruno Darres' turn with his talk titled Code Free Sequence Calculi for Classical Logic.
Thank you, Miguel.
Hola.
Hola.
Hola, Bruno.
Hola.
Adelante, puedes comenzar.
¿Hablo en español o en inglés? You speak in English or in Spanish?
In English, please.
Okay. Well, thank you, Miguel, and thank you all of you for being here. And this talk is called "Cat-Free Sequence Calculi for Classical Logic." This is a joint work with Miguel, with Damián Smuk from Buenos Aires, CONICET, and the Department of Philosophy of the University of Buenos Aires. The motivation of the talk, the aim of the talk is to provide a method to determine, given a cat-free sequence calculus, if it is sound and complete for classical logic. So the aim is to give a method, right? Not to show completeness or anything like that. So the motivation behind the project with Damian is we try to answer this question. What are all the sequence calculi for classical logic? This is a very broad question. So if we don't restrict the form of the rules or the kind of rules or the vocabulary, this is a maybe an impossible question to answer. So the first take on this question was trying to restrict in the following way. We start with a weakening contraction exchange but not cut as structural rules. The language is negation, conjunction, disjunction, and we consider introduction and elimination rules well-behaved. And well-behavedness of rules will be defined in a moment. So this is the question we will answer. Which are all the cat-free sequence calculi for classical logic containing well-behaved rules for negation, conjunction, disjunction? So the plan of the talk is the following. First, I will present what we will consider to be a well-behaved rule, and this will be canonical and co-canonical rules. And after that, I will show how to obtain classical logic. So I will go a bit fast because I don't have too much time, but hopefully I will do it. Well, let's start with canonical rules. Abron and Lev and Lahab and collaborators of the Abron have worked a lot on this notion of canonical rules. And this notion is basically, the idea is that a canonical rule is a rule for a connective such that each rule introduces one occurrence of one connective at exactly one side of the sequence. There are no side conditions or restrictions on the context of the rules. Only the introduced connective and other connectives involved, and the active formulas are immediate subformulas of the principal formula. So, for instance, this additive left rule for conjunction or multiplicative left rule for disjunction are typical canonical rules or application of canonical rules. So the idea of Abron was and collaborators was just to give a name or concept for these well-behaved rules and study the properties of these rules. And Lahab, in his paper, names a sequence calculus containing all the structural rules except cuts and all the operational rules being canonical as semi-canonical. And he gives a semantics for this kind of sequence calculus. And in changing a bit the terminology, the idea is that the semantics of this cat-free sequence calculus is based on this ST notion of satisfaction. So given a tree valuation, we will say that the evaluation ST satisfies an inference or a sequence if and only if either some premise is 0 or 1/2 or some conclusion is 1 or 1/2. In other words, the only counterexample for an inference is evaluation which assigns 1 to every premise and 0 to every conclusion. Well, as usual, an inference is ST valid if and only if every 3 evaluations ST satisfies it. What Lahab proves is to, given a set of sequence calculus and a set of canonical rules, he gives a method to define a non-deterministic truth table for each operation, and the way to do it is just to see how which valuation preserves ST satisfaction. So, for instance, if we have the right rule for disjunction and the left rule for disjunction, the usual rules, the idea is to check which three valuations satisfy preserve ST satisfaction from premise to conclusion. So, as you can see, the right rule for disjunction determines a non-deterministic truth table, which is completely non-deterministic in the case of phi and psi being 0. But in the other cases, it's enough for phi being 1 or 1/2 or psi being 1 or 1/2 to get the disjunction get 1 or 1/2. And dually for the left rule for disjunction. So for each rule, we obtain a non-deterministic truth table. And after that, what we do is to intersect pointwise both truth tables. So this non-deterministic truth table contains all the three valuations which ST satisfy both rules. So this is a method that presents Lahab for this kind of rules in the context of sequence calculus, single calculi without cuts. And so what he proves is that the observability relation determined by this kind of sequence calculi coincide with this what is called the ST locally valued rules over these non-deterministic truth tables. In other words, the evaluation that preserve ST satisfaction. So the observability relation coincides with this preservation of ST satisfaction. Well, our contribution with Damian is to trying to dualize this idea of canonical rules from Abram to co-canonical rules. Co-canonical rules are just like canonical rules, but the inverse of those. That's the idea. So they are like elimination rules. So I will not show these definitions, but basically the idea of these co-canonical rules is that they are elimination rules. Each rule eliminates exactly one connective. No restrictions on the context, no side conditions are imposed, no other conditions are involved, and the formulas on the conclusion, if they are sub-formulas of the formula they are eliminated. So we have two kinds of co-canonical rules. The left example is a cut for negation. So this is a kind of elimination rule for negation. And the right rule, it is the usual elimination rule for negation. And so we are admitting this kind of new rules in the context of sequence calculus. And as before, we call a sequence calculus which contains all the structural rules except cut, and all the operational rules being co-canonical, semi-co-canonical. The notion that will determine the semantics for this calculi will also be the ST notion. So given a set of co-canonical rules, what we do is to provide a method to determine to define a non-deterministic truth table containing all the evaluation that preserve ST satisfaction. So I will put the examples. So let's consider these two rules. These are the usual elimination rules for disjunction, right? So in the first case, we have two rules. Actually, we have two rules. This is yes, an abbreviation, but we have two rules. If we have a disjunction on the left, we can eliminate on any of the disjuncts. And the way to determine to give a truth table for these rules is to read it from bottom to top, trying to get a counterexample. So basically, what you do is to say if I and on the left counter-exemplify the conclusion of the rule, then phi of psi counter-exemplifies the premise of the rules, and the only case, as I mentioned in ST, satisfaction of being a counterexample is to have 1 on the left and 0 on the right. So in the case of elimination rules on the left of the disjunction, if you read it from bottom to top, you say something like, if phi gets value 1, phi of psi should just should get value 1. That's the only way of counter-exemplifying both. And the same for psi. So, of course, I'm not presenting all the details here, but basically, this is the way, the intuition behind the way of constructing the non-deterministic truth tables. Again, what you do to obtain a non-deterministic truth table for both is to make the intersection of the truth tables. And one thing that should be mentioned is that, yes, no, that I will mention after that. So, given a semi-cocanonical system, it is possible to define a set of truth tables containing all the non-deterministic truth tables for each operation. And again, the derivable rules are exactly those that are preserve ST validity or ST satisfaction over the non-deterministic truth tables that we have constructed in this way. So if we want to combine the rules, because our general project was to start with a given sequence calculus with a bunch of rules, maybe some canonical, some co-canonical. So we have to combine all of the rules, and also we need to combine all the semantics. And something very interesting is that here we just need to make the intersection of all of the truth tables, all of the non-deterministic truth tables. In the case that one slot of the intersection is empty, then, or to put it another way, if you do the intersection of all the truth tables and one slot is empty, then the sequence calculus is not cut-free. I mean, cut is derivable, or the sequence, yes, it is trivial. The sequence calculus is trivial. It proves everything. And this is an if and only if. Well, and we have this result again for the combined system. So, how to obtain classical logic from all of this? In a recent paper with Damian, Emmanuel Gemblat-Negret, and Paul Legret, we introduced all the 3 value semantics for classical logic with the ST consequence relation. What does it mean? It means that if you have a given 3-value truth table and you put the ST consequence relation, we have a result which says that this is classical logic or it is not. What we did with Damian in this work is to generalize these results to non-deterministic truth tables. And basically we have these three types of non-deterministic truth tables. The first one are the so-called monotonic truth tables. The second one is in the middle are the truth collapsible truth tables, and the last one are the falsity collapsible truth tables. Basically, looking at the negation, you can see that in the middle case, the negation of 1/2 is 0, and that's why this is called truth collapsible because the 1/2 behaves as a 1, and the last case, the 1/2 behaves as a 0. But in the first case, we have a monotonic truth table. What we proved is that if we have a combined sequence calculus and we do all the method that we showed before, this sequence calculus is sound and complete for classical logic if and only if the semantics of the rules that we obtain in the way I mentioned before are submatrices 1/2 of one of these three kind of matrices. What is that? Does it mean that the matrix, the non-deterministic truth table that we obtain at the end of the procedure should be one of these three truth tables, but possibly deleting some 1/2 in some slots. So you cannot delete a 0 or a 1, but you can delete some 1/2. If that is the case, then this is an if and only if this is classical logic. So I will finish with an example. Assume you have this bunch of rules. Someone gives you all these rules and asks you, this is classical logic if you add weakening, contraction, and exchange, and identity, of course. Well, at first, you should give well, obviously, all of these are sound for classical logic, but for completeness, it's not obvious at all that it is complete for classical logic. And the first move that you think is, well, I need a completeness proof, and I will go on and do the completeness proof. But what we proved is that actually what you have to do is just apply a simple method, and the answer will be yes or no. You don't need a completeness proof. So the first step is separate the canonical rules and the co-canonical rules. The canonical rules are, yes, those rules and the co-canonical rules. The second step is to extract the non-deterministic tables for each of them. So first you extract the non-deterministic truth table for the negation, the non-deterministic truth table for the conjunction, and the non-deterministic truth table for the disjunction, and the same for the co-canonical rules. Yes. And one thing that is interesting is cut for negation, as you can see in the truth table that determine the negation. If you cut negations only, basically you are determining this for 1/2 should be 0, 1, right? And for all the slot is 0, 1. That's the only thing that it does. That the output of a negation cannot be 1/2. And the third step is to do intersection between these truth tables. As I said before, if you end up with a empty slot, with an empty, yes, with emptiness, the answer is no, because it is either it is not cut free, cut variable, or it is trivial. So it's not a cut free sequence calculus for classical logic. And finally, you have to check if this intersection is the submatrix 1/2 of one of the matrices I presented before. And actually, this is the case. For conjunction disjunction, it is just the middle matrices I presented, and for negation, it is one of the submatrices, the only possible, apart from it. And so, as you can see, the negation of 0 is 1 in the case of our rules, and in the case of our matrices, the negation of 0 can be 1 or 1/2. So this is classical logic. This means that the combined sequence calculus we start with proves exactly the inferences classically valid, and no more than those. And we didn't need a proof of completeness for the system, just a simple mechanical check. Yeah, that's all. Thank you for your attention.
Thank you so much, Bruno. Your topic is very interesting. We will open the floor to our audience for questions. Does anyone have a question? Fabio, please.
Can you hear me?
Yes, perfectly.
I'm my connection. It seems that it's unstable. I'm going to please tell if you are not hearing me. Okay.
Perfect.
Bueno, first question is, what about the implication? It's missing here.
Yes. Yes. One of the main limitation of all of this project is the vocabulary. I mean, I didn't have time to put a slide on future work, but one of the things we want to do is to try to generalize this to a more abstract vocabulary, right? Not only implication, but also a more abstract vocabulary. In some sense, we have some results for the definable implications of the calculus from negation and disjunction or negation and conjunction, but this is not quite general. But thank you. Yes, this is one of the limitations of the approach. We are aware of this, and yeah.
Yeah, the conditional always brings problems.
Yes.
And if you put the last slide when you have all the rules.
Yes.
I mean the last one, when you have all the, yeah, that one. Because I have some confusion, because you have, now you move it now. This is the next one.
Sorry. This slide. Okay. Yes. All the rules. Yes.
Yeah, this one. Because you're speaking about sequence calculi, yeah? And sequence calculi has left and right rules. But here you are talking about elimination left, elimination right, and then this is not a standard sequence calculi. So maybe it's only a problem of terminology, because for instance, your ER rules are certainly natural deduction elimination rules written in the style of sequence calculus, but these are not rules of the sequence calculus. So that's why I'm confused. So you are dealing here with some kind of hybrid systems, yeah? You have some clearly rules of the sequence calculus, classical ones like your IR OR, but these E rules are elimination rules. So you are mixing rules of the sequence calculus which have the duality left-right with elimination and introduction rules.
Yes.
And then that confuses me. And, other point is that you have here a could for negation. You have here a could for negation, but only for negation. And it's not clear to me if when you say could free, but you have this could, then I assume that you prove admissible this could, but if you prove admissible this could only for negation, it's because it has problems in the general case, or I don't know. That's why I'm confused.
Yes, Thank you. Yes, you're right in the sense that it is not so common to deal with elimination rules, because that it's also not so common to ask about the derivability relation of cat-free sequence calculus, because if you look at the derivability relation in a cat-free sequence calculus, you need a semantics which invalidates cat, because cat is not derivable. So if you look at the derivable rules, and you need a semantics which makes invalid cat. And in this kind of semantics, even though in the usual setting, the elimination rules are admissible, so the introduction rules are all we need. In this kind of settings, the elimination rules are still admissible but are not derivable without cat. So adding this kind of rules makes a huge difference in the set of derivables, in the set of derivable rules. And the same for cat for negation. I didn't mention it, but we admit cat for any connected, cat for conjunction, cat for disjunction. This was just an example, but I agree. This some people called it hybrid calculus, not a pure sequence calculus in the style of again sequence calculus, because we are adding the inverse of the usual introduction rules. But yes, all of this is in the context of a non-standard framework. Yes, we are using the framework from Lahab, Ori Lahab, and which investigates this in a paper. This standard sequence systems via non-deterministic multiple value set matrices. Yes, but we should change a bit the terminology, maybe not talk about sequence, or maybe mention this notion of hybrid sequence calculus, hybrid calculus with elimination and introduction rules.
Yeah, or just to give the warning.
Yeah, yes.
Yeah, or put a warning, because you you say that you need a semantics to invalidate code, but then I'm confused again. What do you mean by code free? What are we understanding here with when you say it's code free?
Yes, cat free means in this context that cat is not derivable. So you have all of these rules.
You really need a big warning, because you need a big warning, because in structural proof theory, when you say code free, that means that the code rule is admissible.
Yeah, in this context, it's admissible.
And you are meaning exactly the other in other sense.
In this context,
yeah,
cat is admissible.
That's why I was confused. So you are using
cat is still admissible because
code free means that code is admissible.
Yes, in this context, cat is admissible in this setting. Cat is admissible because you are giving sequence calculus for classical logic. So in some sense, cat is admissible because you are reasoning about the preservation of validity between valid rules, yes. So you never have the premises of cat.
Code free means the usual.
Yeah. Code free means the usual. Means that cat is not there,
okay,
and it's admissible. So cat is not derivable.
Okay.
It's just admissible.
Thank you. Okay.
Thank you, Fabio. Agustina, please go ahead.
Hello, can you hear me?
Yeah, perfect.
Yes. Okay, so I have like two clarification questions, but I start with one. First, I was wondering what would happen if you or if it is even possible to add or contemplate like rules also for truth value constants. So for example, if you add like a 1/2 introduction rules, what would happen in this framework?
Yes. Yes. I didn't mention anything about this, but if you have as we defined canonical and co-canonical rules, you can have rules for the truth constants. The thing is that once you have this kind of rules, you know that you will not get classical logic. So that's the only thing that you will not get classical logic.
Okay.
So we will have a non-deterministic truth table. So to these three kinds of non-deterministic truth table, you should add one for bottom and another for top. And once you add this intermediate rule for the intermediate value, it will not be the non-deterministic truth table a submatrix of any of these non-deterministic truth tables.
Okay, can I ask the second question?
Yes, please, go ahead.
Okay. So when I read some time ago the text by Abron and Lev, my main takeaway was that the motivation for giving the definition of canonical rules and a canonical calculus was to define what a well-behaved connective is and differentiate it from others. For example, with tongue. So one of the motivations for giving like these definitions was the philosophical motivation of differentiating well-behaved connectives from other ones. Does this like philosophical proposal also translate to your dualization?
Yes, yes. So if you look at these co-canonical definitions, I cannot enter into the details because we don't have too much time. But if you look at these items, these basically are the intuitions behind what we think is a well-behaved rule, and basically it's like the dualization of the introduction rules, the canonical rules, and yes, that one of the things we want to avoid is something like to have a connective on the premise and to eliminate the connective on the premise, but introduce another formula on the conclusion, or yes, we want to discard this kind of strange movements of elimination rules. But yes, sure, we have this motivation also. Thank you.
Thank you, Bruno. Once again, we extend our appreciations to
Thank you
Bruno for their valuable contributions to today's discussions. Thank you, Bruno. And thank you all for being with us. The last presentations of the day is led by Isabel Gravalos, and the talk is titled Comparing Amplios System for I don't know, for strong, clean, and Dun Belknap logics. Isabel is here.
Hola, voy a compartir la pantalla. Solo tengo que ver cómo se. Hola, encantada.
Tu sesión en español, si así gustas, o en inglés, como tú prefieras.
Bueno, ya la tenía preparada en inglés. Solo estoy viendo cómo se hace para compartir la pantalla.
Creo que hay un cuadrito con una flecha hacia arriba que dice compartir.
Ah, y aquí está. Tenía puesto. Gracias. Ahí está. So, well, hello. Thank you. I'm going to be talking about comparing, as our host said, Tableau systems for strong, clean, and Belknap logics. Can you hear me well? Yep.
Yes, we can.
And I'll be talking in behalf of Pablo Cobreros, Joaquín Toranzo Calderón, Marina Ciratu, and Javier Viñeta. This is a work in progress that we've been doing in the last months that still has some open questions and some results, especially two that we would like to share today. So our motivation to start this work was comparing the two Tableau systems for many valued logics that Priest uses building up to FDE, and that Cobreros, La Rosa, and Tranquini use for STTS and also K3 and LP. So pre-signed trees will have a very short refreshment, which use the nodes A+ and A-, can give us a decision about the valuation of the inferences of some of the strong linear logics like K3 and LP, but also FDE, which is a thing in its own, and tag trees, which have the tags S for strong and T for tolerant, can also decide on K3 and LP, but do something extra, which is deciding on ST and TS, and also allowing us to decide on the validity of meta-inferences. So both systems do some things that are the same and some things that the other doesn't. So our goal would be to see to which extent its system can be adapted to perform the task that the other system doesn't, and whether there is a nice and neat way to decide on the meta-inferences of signed trees. So our example throughout the presentation will be FDE, but it can be applied to other logics seamlessly to K3 and LP in all cases, and potentially to other ones. These are some of the open questions that we will be mentioning. So the first question would be, can we use tag trees for FDE? And vice versa, although we'll not answer that today because it would take too much time. Could we use signed trees for ST and TS? But we're going to focus on the direction from tag trees to FDE. And if we extend the signed trees, could we use them for the mixed analogs of FDE and possibly talking about their meta-inferences? So the introduction will be a brief refresh on side and tag trees. Then we will talk about the equivalences between them, and the translation that we have designed. And then we'll present the mixed Thun-Belknap logics, which are the semantics within which FDE is, and our possible meta-inferential tree calculus. So as for signed trees, a quick refresh, our initial list has all the premises with an A and all the conclusions with a B-, where A means that our premises are related to truth and minus that they are not. And then depending on the closing conditions, if we use the pure unadulterated A+ and A-, we get FDE. And if we use, for instance, not A and not no A, as in not related to truth and not related to truth, we would get the logic of paradoxes. If we work on the related and not related to truth side, we will get K3. And to build the trees on them, we will use, these four are only an example. We will need the rules for conjunction, but of course as well for disjunction and negation. So this would be the sign trees, and an example here. We got our premises A and no A implies B or no B. So the premises with a plus, the negations with a minus, and eventually this tree, which does not close for FD because we do not have the exact same formula with either plus or minus, actually does close for LP and K3, because we do have B minus, no B minus. Here you can see the mouse, right? And also a multi-method with a plus here. Because those LP, and K3 are paraconsistent and paracomplete. So this would be an example for building like the most basic tree for FDE. And this would be how we build the ST trees. Our initial tree will have, so in this case, we will have X and Y as possible locations for strict or tolerant tags. And our D function would be a tag switching function. So if we have on our premises a T or a S, we will maintain the same. If we have in the conclusions either a S T or a S, we will put the dual of it, no, and the other tag. And we have four closing conditions. The last one is empty because it would be for TS, which is an empty logic. And we have here LP K3, and the novelty would be TS, which closes with AT and no AS. And then again, the rules, which would be all the rules for conjunction, disjunction, etc. And this is just an example to not make this too long. And here's an example of the application of the rules where we are working in tolerant logic. So here we can see that the S is where we have applied the D function. So we get the premises no B or no B S. The TT would be priests LP. And this closes for it. And it would close for K3 as well, but not for TS. And again, very basic example, but the one thing that the tag trees do that the sign trees don't would be get to this extra level of the meta inferences. So to build our trees for meta inferences, what we do is we build the rules for both the satisfaction of each logic. In this case, we have by now 4, and we could extend it to a third one, fifth one, which would be FD. And also the rules for the counterexample that, of course, if you notice, are exactly how we build a tree for the inference level of that logic. So we would have the initial list where the premises would be the rules for the satisfaction, and the conclusions would be the rules, or say the whole tree for the counterexample. So then again, we have an example here. This would be proof of lack of transitivity of ST. So we would have the two premises with ST just as they are, and the conclusions as the counterexample. Once we build the tree, we realize that it has in fact one open branch and ST is not transitive. But it would close for TT or LP, SS or K3 and TS. Which of course it's not empty because we are now in the meta-inferential level. Now, once we have that, our next step would be to say, all right, so we got the sign trees that work for FDE, but not for the meta-inferences, just as we saw in the previous step. And not, especially if we want to extend it to the whole of the Dunn-Bellman semantics. And then we have the tag trees, which are designed for the strong cleavy logic and only for 3-valued logics, but not for FDE, which even though it's in a 4-valued environment, only preserves 2 truth values, 1 and B. So we already have a structure in which that might work. So can we adapt the tag trees for FDE? Could we extend the sign trees for these meta-inferential levels that we were talking about before? And to be able to decide on meta-inferences that could give us extra information about the logics. So yes, they can be adapted. And the strategy would be to design a system of, in this case, it says tagged dagger trees and signed dagger trees. We only use each one of those for one of the directions of the translation. Now we're gonna go from tag, sign to tag. Yeah. And then the other direction will be a mirror proof of it, almost the same, but if we get the gist of it, it's easy to see how it would work. We would see how tagged dagger and signed dagger are equivalent to regular tagged systems and regular signed systems. And then we see the translations of the whole trees from, and this is the relevant part, for tagged trees to signed dagger trees, that's one of the directions. And then from signed trees to tagged dagger trees, that would be the other direction. So each one of the extra systems will be used only for one direction of the translation. And then we'll double check that indeed those tag trees can be translated to the closed ones that the closing conditions match. And since we will have established from the beginning that tagged dagger trees and are equivalent to the tag trees and signed dagger trees are equivalent to the signed trees, if there is an equivalence between tagged and signed dagger and signed and tagged dagger, then we'll be able to conclude that tagged and signed trees can be equivalent. So these systems that we're introducing, what they do, they introduce only these 2 extra rules. In this case, we're working in the direction of tag tree. And as it can be seen clearly on the slide, these 2 rules don't actually add any extra information. We know by looking at the first rule that we could first apply the double negation rule, and then we would be able to have A and B in one single branch, A and underneath B. And if we apply the double negation to the disjunction, we would have A or B in the 2 branches without the double negation. But the reason why we need this is because when we're translating, in this case from the signed trees, we will need to keep the structure to be able to translate node by node and to prove that they are indeed equivalent. But it's easy to see already that the tagged dagger trees are definitely equivalent to regular tag trees because these two rules don't add any extra information. So an example of the translated trees would be the one on the right would be an example of the application of the sorry. So two instances of the use of this extra rules. In the first one, we just skipped the double negation altogether, and in the other one, we're doing it afterwards, which is kind of unconventional, but then again, we see that it's equivalent. And in the opposite direction, that's interesting because even though we're not going to use it, we can see that the mirroring of the rules in the first system, the rule that was not branching was the conjunction, and the branching one was the disjunction. And in the other one is exactly the opposite. So we'll have a non-branching disjunction and branching conjunction. And so our initial list will be the same. But one extra information, one extra step that doesn't add extra information would be that we will often see it closing with double negations as well. And then again, since this doesn't add any extra information, we can see that sine and sine dagger trees are equivalent. So after that, we would use a translation function, tau function. So if we're translating from sine trees, every time we have a plus sign, we would translate it as strict. Every time we have a negative sign, we will translate it as not the formula and t. So the pluses always stay just as they are. The negatives are always translated to their dual. And the same in the other direction. If we were to start with an S tree, if we were translating from from tag trees to sine trees, we would get the A plus anytime we have this, just as it is. But when we do have a T, we'll have no A minus. So that would be our dual translation. So we would use our translation tau 1 or 2. In this case, we're going to stick to 1 because we're working with FD. And with those, we can translate all the initial lists. We have here, we have both yet. So we can clearly see how this would work. We can see also the other direction of the translation. And that's when we get that, because for instance, in SS, for instance, or TS, we would get negative T's. When we translate it to sine trees, we start to get double negations, which of course are still going to close in the same places. But that's the reason why we're going to need the extra rules to be able to translate node by node every time something like that happens. Crucially, we need to translate all the rules. Here I'm showing only some. These are the conjunction. This is where we have the special one. These are the disjunctions, where all of them are the same, but when we see the translation from sine trees to tag trees, we can clearly see why those rules appear. And these would be the negations, which will also have like extra rules for double negation, extra negative signs because of the tau translation. But we can see here that they're all equivalent. So basically, what we're proving here is that for every signed system, we have a signed tagger system. They're equivalent to each other, same with the tagged ones. And we can translate from the tag to the signed tagger, from the signed to the tagged tagger. So indirectly, we conclude that signed and tagged are equivalent, but always going through these extra steps. Now, going on to the third and last part of the talk, we jump a little bit to the mixed dumbbell map. In general, dumbbell map semantics to which FDE belong. We mentioned FDE was the one that preserved 1 and B, but we can have all sorts of combinations with it, with the 4 values, 1, neither B, and 0. Or preserving 1, neither, and B, if you wish. So Vintine in particular studied all of those at the inferential level and gave some very detailed insights on many of them. But what we are gonna try to provide is an extra way, a way to go an extra step beyond and decide on the validity of the meta-inference level for those. So this would be a chart, super basic, no weird names, of all the combinations of the possible truth value preservations of dual-developed semantics. The ones here in the diagonal, DB1, 6, 11, and 16 are the ones that are not mixed. For instance, DB11 would be FDE, so we can see here it preserves 1 and B from both sides. The one that preserves 1 and 1 is the exactly true logic that has been studied by Getz and Rivecchio, which also has very interesting properties. But all of this are different combinations that we could actually go into Weinstein's paper or just looking at it, realize which ones belong to potentially K3, OP, even STNTS, or maybe other logics that are not named. But all of this above and beneath the diagonal would be the mixed logics. So a way to express how to visually see this chart is creating a lattice. And the values that we're going to give each one of these preservation values in the sign trees would be for whenever A is related to truth, as in 1 and B. We just look at this set here. When it's not related to truth, 0 and N, there's like other black lattice here. But when it's, for instance, not related to, not formula, but related to truth, like in 0 and B, we have here the red set that will show us how to name our and build our trees with no A plus. And for not related to truth, which would be 1 and B, we have here the other red set. And it will help us build any of those 16 logics quite easily. And so above very visually. So the idea is to follow the same rationale of the extra step for the meta-inferences that we saw at the beginning of the talk that was used for tag trees, and try to do the same to find the satisfaction and the counterexample rules for each one of those 16 logics. And then again, our example right now is FDE because it's better known by everyone, where basically, of course, it's a consequence relation. So if we want FDE to be satisfied, then it's either not related to truth. The premise or the conclusion is true, which in FDE means related to truth. And the counterexample, which is the same, has the same structure as the tree for the inferences of FDE. So we get to the example. One important caveat, though, well, not a caveat, a thing to be noted, is that this gives specifically the local validity. So, which is interesting completely in itself. But one of the open questions that we have as well is whether we could look for a system that would give us also the global validity. All of this, everything that we're gonna talk about now, is local validity for the meta-inferences of these two kind of logics. So an example, all right. So FDE, we know it quite well, and now we're gonna try and see how to build an example. So we are starting with exact truth logic, which we have already mentioned, and also this one is also symmetrical, so it's a bit more easy. So we start building our satisfaction rule. This A is in bold. We realize that if they have to be anything but one true, then they can be either A minus, not related to truth, might and R0 or black set here, or related to falsity. Oh, sorry, that's N and 0, not related to true, B and 0. So using our lattice as a reference, we get our first two branches. Because there are two sets, we get the choice between the two, so there are two branches. Then we get to a B that, in this context, has to be exactly one. So it's the intersection of these two sets. And we will get B plus and no B minus in a single branch. Going on to the counterexample, we know that A has to be exactly one, so we follow the same idea with this bold A's in here. And for B, once again, for the counterexample, we will have a branching option. It can be either neither, both, and 0. So with all of that, we build our rules for any tree that will give us the decision of the validity of the meta-inferences for ETL. Now, going to a mixed example that's probably more interesting. This is DB8 for no particular reason, just because it's interesting. It preserves neither on one for the one side and neither both and one on the other. So we can see first we have our neither on, it doesn't have to be neither on one for the consequence to be preserved. So we can see quite visually that it's going to be the red set here, not A plus. Our B can be anything, neither, both, and one to be true. So we have the choice between our two sets. Therefore, this is our tree will start with 3 branches at the very beginning. And then we have our counterexample rules with our purple A, which N and 1, we already have it preserved here. And the conjunction of B minus and no B plus, which would be exactly 0 for when our conclusions have to be anything but N, B, and 1. So with this, I think it's quite visual how we can build any possible tree for any of those 16 dual-brain semantics. And just to finish, here are a couple of examples of them at work. So we can see this is FD again to see it clearly. Looking at its transitivity, which it is transitive, it would build starting with A and B, B and C, and the counterexample, and it closes quite nicely. Just to have a different view of it, here's DB3, which has to preserve 1 and B and 1. So we start to have different mixed rules. Indeed, we get that it is not transitive, which is quite logical. It's a tree that branches quite fast because we have many options. And the counter model would be whenever B is related to both, A is related to 1, and C could be either neither or 0. So it's the one that's not related to true. This is it. This is an example of how we can apply this to build any kind of meta-inference rule. So like I already mentioned during the talk, we end up with these 2 open questions. If we can find a system for global meta-inferential validities. And also, we already mentioned that even though we haven't shown the translation, we can translate ST and TS to sign trees. But the question remains, how many of the Dunbell map semantics can be translated to tag trees? Because of course, they have only 3 values. Or if we could extended version of it, that even though it wouldn't be completely equivalent, it could be helpful in the sense of being more simple or more elegant and just using a different notation to convey the same thing. But ideally, and first, to see which of all of those can be translated to tag trees. Probably only 9, but I can't get ahead of myself on that because they're going to scold me for going too fast. So these would be the things that we still have work ahead of us. Thank you very much.
Thank you so much, Isabel.
Can you hear me? Can you hear me properly?
Yes. Yes, I can hear
okay,
you.
Perfect. Thanks a lot for the presentation. It's a very interesting project. And I just want
Thank
to...
you.
I'm curious, I'm curious about the advantages of your approach regarding the meta-inferential territory. In the sense, I'm not that familiar with meta-inference bibliography that you mentioned, but what I see in your Tableau is that in the end you evaluate at the formula level, right? I mean, the rules decompose till you reach the very formula level, or right? I mean, it's you reach the inference level in at least in your example. Probably
Eventually,
you can,
yes.
eventually. Okay. So how I read this? Because I mean, you can close a branch before, right? With other kind of signs, for example, referring to meta inferences that are, so to say, incompatible, right?
Mm-hmm. Of course. And then you wouldn't need to reach the formula level. You could, but maybe it closes before you.
Okay, perfect. So it's just that you need to add more. I mean, you didn't tell us here for brevity, you didn't mention these rules, but you can close it before. So it is, so to say, more compatible with this meta-inference idea of, okay, I understand that. And another comment, sorry.
Just as a follow-up, even if they don't close before, because you have many more branches, because you've started with both the satisfaction and the counterexample model, even if they do close at the level of formula, they close, for instance, with a combination of, well, no, wait, I just said something absurd. But yeah, I mean, you can end up opening extra branches underneath that close at the formula level that wouldn't have closed in not inferential tree, just because you have so many more formulas nested on top of it. Even if they close at the bottom, you can still get different results.
Okay,
And
perfect.
Can
I go ahead with my second question then? I assume yes. Well, okay, so
yes, I'm just muting.
yeah. Okay, so the second question is it's I do care about the relative complexity of systems, meaning that I do care about the size of the proofs within one system and another one. So I mean, intuitively, the maps that you do between target and signed tableau, like it seems to me that they preserve the size of the proof of to a polynomial. I mean, I don't want to sound too technical, but the idea is just that in computational terms, your systems are equivalent as far as I see. But I don't know if you are also investigating the efficiency, the computational efficiency of the systems. If you are comparing praise and your systems, is there some ongoing research about it? I mean, like comparing their computational efficiency?
So we have talked about it, but we haven't gotten there yet. But they're pretty similar though. The difference wouldn't be huge, although sometimes, you know, when things just add up exponentially, they can mean a lot, but they're very, very similar. And if you're using the extended versions, then they're completely similar. It's more about first about which one was easier to see and if it could help the understanding of the philosophical meaning of the logics, or at least the underlying structure. And then it has been more like something like being inspired by how tag trees work. Let's see how we can extend sign trees. But computationally, they're very, very similar. And it's interesting, for instance, if you were to build a program looking at the validity of the inferences, that you could add any of the two, that you could maybe use the more efficient one. But there wouldn't be a big difference, I think, unless you're looking at very, very, very big inferences. And in each case, one of the sides of the translation would systematically be the shorter one, the one that's not the extended version of the system. But you would really have to actually do the tree before seeing which one is which one is more efficient. So it would be like a double check for the program. They're very similar.
Okay, thank you very much.
Please go ahead, Agustina. Please go ahead.
Sorry, can you hear me? Yes. Okay. So Isabel, I wanted to ask you if this proposal that you have with of the tableaus, is it does it go like beyond the meta inferential level to, for example, like meta inferences and so on?
Yeah, you could nest it up as much as you wanted. You would always be building the counterexample and the satisfaction rules for each level. But yes, of course, you can nest them up as much as you want.
I have a small like suggestion for the global validity question that you put out. So
that'd be super interesting.
Maybe instead of like giving rules for proving when something is globally valid, you can have like something of the sort, or either the premises are an open subtree or the conclusion is a closed tree or something like that. I don't know, maybe it works. I was thinking that.
We would have to check that in detail slowly. But yeah, I'll take note of it. It actually makes sense.
Okay. We express our gratitude to Isabel. Thank you so much, Isabel. And
thank you, Miguel,
for your participation in this wonderful event. We remind you that tomorrow we'll continue with in-personal talk. See you then. Ciao.
Gracias, Miguel.
Thank
Chao.
you. Bye.
No.
Thanks.